Hi everybody, Physics Ninja here. Welcome to my video on calculating the electric field from a cylinder. This is the problem today. I have a cylinder that is uniformly charged over its volume. And the goal today is to calculate the electric field it produces at some distance away from the cylinder. Now, in order to solve this problem, I'm going to proceed two different ways. But we first have to be able to calculate the field produced by a ring. Once I have a ring, or I know the field produced by a ring, I could do two things with that. I could either make a shell composed of a whole series of rings, or I can make a disk. Okay, and those are going to be my building blocks to calculate the total field produced by the cylinder. Once you know the field produced by one shell, all you have to do is consider a whole series of shells with different radii and add their total fields to get the insulating cylinder. Likewise with the disks, once you know the field produced by one disk, I can create a cylinder simply by slicing it up into multiple disks. Now each one of those is a different distance away from the point P, so you have to integrate the results, but I'm going to show you how to do that today. Alright, so this is kind of a nice video. We're going to show you both methods, and at the end we're going to get the same result. We have to have the same result, but it's interesting to see the different approaches. Alright, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. I've also recently launched my t-shirt store at physicsninja.etsy.com. Consider getting a t-shirt to support Physics Ninja. Alright, let's get started. Alright, so for part one, what we're going to do is starting off by considering the ring produced by a uniformly charged ring. Once we know the electric field from a ring, I am going to construct a shell by simply adding up a whole series of rings that span a distance L of that cylinder. Once you know the field produced by one shell, all you have to do to construct a cylinder is consider a whole series of shells, infinitesimal shells that span this whole volume here inside that cylinder. And that's how we're going to get to our final expression for the electric field produced by a cylinder. Alright, so this is how my setup is. I'm going to first consider the ring. The total charge of the ring is some positive charge Q. The radius of the ring is R. And say the distance here from the center of the ring to a point where I want to evaluate the field, I'm calling that X. I've also defined this angle theta here in the figure, and that's simply this angle here. Okay, so the first thing you have to do is, if I'm only considering this little bit of charge dq here that I have denoted in red, the first thing you want to do is simply define, well, how big is the field produced by this little bit of charge at that point? And that is simply the expression from a point charge, except now we're considering an infinitesimal charge dq. Now the distance r is the distance along this dashed line here, and that distance r you can simply write in terms of these other variables. Just use Pythagorean theorem. That is simply x squared plus r squared, and take the square root of that. Now again, if this is a positive charge, what you do now is, let's consider the vector that it produces. It produces a vector of magnitude given here in this first expression. However, let's just put that in the figure. And that vector I can also break down into two components. There is an x component and a y component for only that one little bit of charge dq. Alright, so the next thing you want to do now is, let me just substitute that r value here into my expression for the magnitude of the field, and that simply looks like this. Now, we don't only want the field produced by one little bit of charge dq. What you want to do now is add up all of the field components. When you go around this ring, each little charge on this ring produces the same magnitude of the field because it's always the same distance away from the point. Now, there is something you should note from this problem, and this is a really, really important point. Every time there's a positive charge dq at the top of the ring, there's an equal charge here at the bottom of the ring. And you should be able to see that from symmetry of the ring, that once you add up all of those contributions, that the total field in the y direction should be equal to 0. This is a really, really important point for this problem, and it's a simplification, right? And this is only true because we're considering a point that is on the axis, right? It's on that central axis of that ring. If we were at any point that is offset here, Along the y-axis, for example, that would not be true. All right, so what we want to do then is we want to really find what is the x component of that field. So the first thing I would do, well, let's figure it out. We have a nice triangle down here. I can write dEx as being simply dE multiplied by cosine of that angle theta. And from all of that information inside this triangle, we also know that cosine of theta here is simply x divided by r, and I have my expression for r right here at the top. So what we have to do here is just go back and substitute in here. Substitute the cosine of theta into my expression for that infinitesimal field component dEx. So we substitute everything in here. Now we see we have similar terms. Now they have different powers, however we group them all together, and here we're going to find that dEx is kx multiplied by dq, that infinitesimal charge, and divided by that factor to the 3/2. All right, so this is a really, really important equation. Now what we want to do is we don't want just one infinitesimal field. We want to include all of the fields produced by all of the charges. So we have to set up an integral for this expression. All right, so we start with our expression. Now we want the total field in the x direction. So we simply have to integrate this expression. Well, we substitute here inside the integral. We substitute all of this equation here in the red box, and this is what we get. Now, we have to keep in mind that a lot of these terms inside this integral, they are constant values, okay? X is a constant. It's the distance from the center of the disk to the point where I'm evaluating. The radius is constant. Therefore, all of these terms can be taken outside of the integral, and that's a huge simplification for this problem. So the integral here boils down to this. And all we are doing here is we simply have to add up all of the charges of the ring. That is what the integral of dq gives. So if you integrate that, you simply get our final expression, which is that the total x component of that field is kx multiplied by the total charge of the ring and divided by this distance term. Okay, that is our fundamental building block here for the rest of the system, but this is the field, or the x component of the field produced by one single ring that has a total charge q. We'll be using this result a lot going forward. All right, the goal now is to find the electric field at point P, as shown in the figure here, produced by a shell, okay? And now the total charge of the shell is going to be some positive charge q. Okay. This shell here has a length L. Again, will have the same radius as the ring that I previously considered, which is R. Okay. Now, what I want to do here is I'm going to consider that a shell is simply made up of a whole series of rings. And if I know the field from one ring, what I have to do to get the field from the shell is simply add up all of the various rings going from this starting position to the ending position. That's it. All right, and really the whole point of this is to use the previous result. How do I change it now to include all of the rings? And how do I perform this integral in order to get the total field produced by the shell? All right, so we now want to construct a shell and find the total field produced by a shell at this point P. So here's the geometry now. The distance D is a distance here from the end of the cylinder here all the way to the point P. The shell has a length L. And now what I'm going to do now is I'm going to construct this shell out of a whole series of rings. Each ring has, I guess, a width here called dx. And how would you apply now our previous result in order to find the total field produced by the shell? Again, the shell is simply made up of a whole series of rings. However, each ring now produces a different field because its distance, if you look at here, this distance x, is going to be different, right, for each ring. So we're still going to have to perform an integral. However, we could still use this result because it's going to help us simplify that calculation. Now, there's one important point here is that in my previous result, I had the total charge of the ring here inside the field expression. Now, clearly, the charge of this small ring, this infinitesimal ring, cannot be big Q. It has to be some other value, which I'm going to call dq. And dq is basically taking this whole charge, the total charge of the shell, and slicing it up into infinitesimal amounts. So that's the first thing we have to do here is we have to find the charge of the ring. Okay, and I'm going to write it like this. I'm going to write it as dq equals to q over L. Q is the total charge of the shell. L is the total length. And now I simply have to multiply by this little bit of thickness here, which I am calling dx. Okay, so this is going to be the charge of that ring. Okay, this is a really important point. And this kind of looks like a linear charge density, right? This Q over L, you might define that as being almost like a lambda that you would see for 1D charge distributions. So now what we do is we write the field due to just this infinitesimal ring that has a charge dq. So you take your previous result and you substitute dq into that expression. And now, well, let's go ahead now and write it in terms of the thickness dx. So I eliminate dq by using my charge expression. Okay, there you go. And now what we have here is now you can see we will have to perform an integral in order to evaluate this field. If I am looking for the total field in the x direction here produced by this entire shell, what you have to do is you have to add up all the contributions due to all of these rings. All right, now we have to think about this a little bit. So once you integrate, these are going to be the limits of this integral. I'm going to integrate here from d all the way to d plus L, right? That'll include all of the different rings that I'm considering that produce a field at this point. All right, so all we're left with now is to evaluate this total field expression. So we're going to go on the next page and finish this calculation. Okay, so here's the expression that I want to evaluate. The first thing I like to do is just remove all the constants, bring those all to the front so we don't have to worry about them anymore. Okay, now you're left with this expression of x dx over x squared plus r squared to the 3/2. All right, this actually isn't too bad an integral to perform, and you could do it analytically. So let's just follow just some of the steps that I would do. Here I'm going to simply define u as being the term in the bracket down below as x squared plus r squared. If I differentiate that, I can get an expression for du equals to 2x dx. And now that's kind of nice. So it's just the u du type of substitution. So you have x dx then that equals du over 2. All right, so I can rewrite this integral, but before doing that, let me also just change these limits. Here, x goes from d all the way to d plus L, the way I've defined it. And that means that the initial u value will go to d squared plus r squared, and that the final value here, you substitute d plus L into my equation over here for u, and this is what you get. So certainly the limits got a little bit more complicated, but the rest of the integral is going to be a lot easy to evaluate. All right, so this is what we have, and now we simply write it as a u du substitution, and this is what it ends up being. And this is a nice, easy integral to evaluate here because it's simply going to be, this is pretty standard, right? It's u to the negative 1/2, which I bring the 1/2 or the u to the bottom, and you get these factors of negative 2 that comes from the integral, and that cancels with the 1/2 factor from the front. And now you simply substitute the limits inside this integral expression, and this is what you're left with. And now at the end, I just want to go back and just substitute these two limits here to get it in terms of the parameters of the model, which are d, the distance d, and the radius r. So at the end, this ends up being the final expression for the electric field produced by the shell. Okay, and the shell again had a length L, and I was a distance d away from from one of the surfaces of the shell. Okay, so this now is going to be our starting point for the next calculation. What I now want to do is I want to consider a whole series of shells in order to construct my cylinder. All right, so now what we're doing is we're considering a whole series of shells to make up our cylinder here. Pretty straightforward. What we need to do is you need to find what is the charge on each one of those shells, just like we kind of did previously, right? Because the total charge of the cylinder is big Q. Now we're going to define something called a volume charge density. This big charge Q is distributed uniformly across this insulating cylinder. Okay, so I can define the volume charge density as being dQ over dV, and that's simply the total charge divided by the total volume of that cylinder. The total volume is just this area multiplied by the length, so pi r squared multiplied by the length, and that's simply a constant value for this cylinder because it's uniformly charged. All right, now what you need to do now is find how much charge would there be on any of these shells, because the shells are going to have a different radius, and this is kind of what it looks like, right? If I just consider an inner shell here, it would have some radius r, and it might have some thickness, which I'm denoting as dr. So if you wanted to find how much charge is on this interior shell, I'm going to call that dq. Okay? It would be, well, the charge density, the volume charge density, multiplied by the volume, right? And that volume of this shell is simply going to be the area of the shell multiplied by the thickness, and the thickness is denoted as dr. This area of the shell, notice what I have is I have 2 pi r, that is the length or the circumference of the shell, and then multiplied by the length. Okay, so that is an important expression here, and that tells you how much charge does each shell have. And now you can see we're going to have to integrate our field expression. We're going to have to integrate over all the different radii of these shells. So let's go on the next page and finish off this calculation. All right, so here was the result for one shell. Well, now we want to do the result for one shell, but it has a smaller radii. So what we have to do is substitute, change the big R for a little r in this expression. Now, the other thing we have now is we didn't have, each shell has a small charge dq, so that's why I've changed the total charge q for some total charge dq of the shell. Now what we're going to do is go back, and we had an expression here for the amount of charge on each shell. That was rho times the area times the thickness. But we had an expression for the charge density also, because that was simply the total charge of the ring divided by the volume. So if you go ahead and you can simplify those terms a little bit, that simplifies to this for the total charge. You go ahead and you substitute now that into my field expression for a single shell, and this is what you get. Now this looks rather complicated at this point, I agree, but let's not worry too much about it. All we have to do now is perform this integral, because we want the total field produced by all of these shells. And we're integrating over the variable r, and we're integrating from 0 all the way to some maximum radius, because that's simply the radius of this cylinder. All right, so what we have to do now is simply perform this integral. All right, so we have integral to perform. There's really two terms here in this integral. However, both of them are rather similar, other than this second one has an extra factor of L there. It doesn't lead to any more complications. You can see that both of these can be done using a UDU substitution. Okay, so this is what it looks like. For example, for the first term, I may substitute U as being D squared plus R squared. For the second term, I do something similar, except it's D plus L squared plus R squared. The DU terms look exactly the same, and now you can substitute the UDU terms in there. This is pretty straightforward. So the first term of this integral looks like this. You perform the UDU substitution. I'm going to skip a couple steps here and just show you the final result. Just evaluate it for yourself. It is pretty straightforward. I've highlighted the approach here for you. You should be able to do this by yourself. All right, so you do that. Now you substitute our limits of integration. That is the first expression. Now we still have the second term to deal with. The second term here is like this. Again, we use a UDU substitution, and you get a similar looking term that looks like that. Now to get the total field, you certainly have to combine both of those terms together. There's no escaping that. So we go ahead and you combine both of those terms. Now, there are some simplifications that are going to happen here, a couple of them, and then you get to my final result. My final result looks like this. Now, it's a rather complicated looking expression. There are 3 terms over here, and that's okay. This is the final expression for the field produced by a cylinder that has a total charge Q and a radius R and a length L. All right, so this is the first approach. Now, what we're going to do is we're going to recalculate, except this time we're going to use our ring result, construct a disk, and then add up a whole series of disks. All right, so this is the next approach. I'm going from the ring to form a disk. All right, and the goal is to combine a whole series of these rings in order to find the field produced by a two-dimensional disk. So this is what one of those rings looks like now. It's going to have a radius r. It has a certain thickness, which I am calling dr. The goal really now is to find how much charge is on one of these rings, because the total charge of the disk is big Q now. So what we're going to do is you define a surface charge distribution. I call it sigma, and that's the total charge of the disk divided by a total area. And that's simply equal to dq over dA, and dA is the area here, an infinitesimal area of one of these rings. So the area of one of these rings is going to be the thickness dr multiplied by the length of that ring, which is 2 pi r. So that's why this denominator here looks the way that it does. All right, so go ahead and just rearrange this because we really need to find how much charge is on one of these rings. So that value is dq. So you go ahead and I substitute in everything here. So I have the sigma, which is the total charge of the disk divided by the total area, and then multiplied by the area of one of those rings. Next thing you do now is you go back and we substitute, right? You substitute that value of dq inside our expression. Now the big R now must change to a little r because I have to consider a whole series of these rings and they all have a different radius. Now again, I substitute the value of dq with what I found over here. I cross out some of the constant terms. And now I am ready to find the total field because now I have at least the field produced by one ring can be written as this expression. And now all we want to do is you want to integrate this expression. You can see we're going to be integrating over the radius and we're integrating over the range of the radii. And that goes from 0 all the way to the radius of the disk that I'm considering. Okay, so here's the integral expression that I'm trying to evaluate. Again, you're integrating from 0 to the final radius to get the total field produced by one disk. All right, you can look at this form of this integral and guess what? This is going to be another u du type of substitution. So I define u as being this denominator term here inside the bracket. You can easily evaluate du. Again, you have to change the limits of the integral. We proceed the exact same way as we previously have. Everything ends up being a little bit different, but still it's a similar approach, right? So you're integrating 1 over u to the 3 halves. That's a very straightforward integral to evaluate. Go ahead and do that. Substitute the limits of integration inside my expression. Just be careful with the negative signs and the factors of 2's. And go ahead here, and at the end of the day, we get an expression that looks like this. You can write this maybe a little bit differently here. Just multiply through by this x term, and this is kind of a more standard approach here. Yeah, so we get, this is my total field produced by one disk, okay? So remember that if you wanted to, you can also write this in terms of the charge density of the disk. The charge density was Q over pi r squared. So this expression can also be written in terms of that sigma value. Again, just getting rid of the charge and multiplying, getting rid of the charge by using the surface charge density here. So here's the final expression for the disk. And now all you want to do is, well, consider a whole series of disks in order to find the field produced by a cylinder. All right, let's go finish off the problem. Okay, so we're now going from disks to a cylinder. Again, each disk now produces a field at that point that is given by this expression here. I just kept it in terms of dq over here. That's going to be a nice variable for me to make this substitution. Okay, so that is the infinitesimal now produced by one of those disks. And one of those disks is a distance x away, but there's a whole series of disks here that I need in order to produce a cylinder. The next thing you want to do is you want to figure out now how much charge is in each one of those disks. Again, since the total charge is Q of the cylinder, what you're going to do is simply slice this cylinder up into a whole bunch of of disks. Each disk is going to have the same thickness. Maybe I call it dx. So I can write this linear charge density here, the amount of charge you have per unit length, as being the total charge divided by the total length. Again, this charge is uniformly distributed right here. Now what you end up doing again is you substitute. So dq, you can write it as q over L multiplied by dx. And you're going to substitute that expression up there in the integral, and we'll have to perform one more integration over that variable dx. All right, so here's my expression for the infinitesimal produced by one disk. That was the amount of charge on one disk. Again, we want the total field now produced by all of the disks, so we integrate. And the variable of integration is dx. And now dx goes all the way from d, that's the closest disk to me, going to the farthest disk, which is d plus L. Okay, and I have to integrate this expression. Now the first one here is pretty straightforward. That's an easy integral because all these other terms here are constant values. This second one right here, well, guess what? This second one you can do by using a u/du substitution. That seems to be the theme of the day right here. So again, using that same approach, you do a u/du substitution. The first integral ends up simply being x evaluated between d plus L and d, so that you're only left with that length L. And now this second one gets a little bit messier, but it still is doable using that u/du substitution. You go ahead and you evaluate that, and this is what you get. And guess what? This is the exact same result as the shell method. All right, so kind of a really, really nice problem. I worked on this problem with a student. I thought it was just a good problem, and I wanted to share with you two approaches to finding the total field produced by a volume charge distribution, right? You could either break it down into more fundamental units, right? Like a ring. From the ring, you can either build a shell or a disk. And from those other objects, you can build more complicated shapes, okay? Like a cylinder. Anyway, hopefully you appreciate this video. We'll see you next time.